Welcome to Let's Get to the Marks, going through Group 7 A-Level Chemistry, AQA, one of them walkthroughs from the amazing PMT website. So let's go. This question is about chlorine. Chlorine has a low boiling point because the forces between the molecules are weak. Explain how the forces arise between the molecules of chlorine. So what we want to look at here is chlorine is a diatomic molecule, so it has two atoms. They are covalently bonded to each other. Now, the electrons, there is a cloud of electrons spinning around these chlorine atoms, and occasionally, just by chance, that cloud of electrons might be, at any 1 millisecond, closer to this chlorine atom than that chlorine atom, and that was a pretty rubbish drawing for it. You might want to draw it something like that. Okay, so the cloud of electrons, the probability of an electron being found is higher over here in that millisecond. That makes this more negative. We call it delta negative, and this slightly positive. What happens is, in a bunch of chlorine gas, you're going to have a whole load of chlorine molecules. And this slight negative charge is going to repel the cloud of electrons over here so that they are like this. And that is slightly negative, and that is slightly positive. And what's going to happen is a weak form of attraction is going to form between this delta negative chlorine atom in one chlorine molecule and the adjacent chlorine molecule, a delta positive chlorine atom on that one. That is a temporary attraction because guess what? With these weak forces, they are constantly forming and breaking millions of times a millisecond. So literally that bond will form, and within the next few seconds, few moments of time, I don't really know how long, the cloud of electrons will change their shape, and it just so happens that maybe this will have more electrons over here, and this one will have less. And so this becomes negative, this end of the molecule, and this end becomes positive. Guess what it does there? It then repels this electron cloud. So it's really the interaction between the electron clouds between different chlorine molecules. This one is then going to become positive, and we're going to get another attraction going on there, but it's constantly breaking, repelling, attracting, repelling, very weak forces of attraction. Anywho, we just need to put this into words. So what we want to say is da 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 da. So how I want to word this is, how does this dipole first of all set up? Well, it's due to the random movement of electrons. So I want to say random movement. Oh, I'm typing in blue today. Random movement of electrons creates a dipole in a chlorine molecule. Lovely jubbly. That's our first marking point. So you can just say there's an imbalance in the distribution of the electrons. Anything that describes that, which creates a dipole. One chlorine atom is slightly negative, one is slightly positive. And we could sort of say that. Now, what happens is this has an effect on the next chlorine molecule. We call the next chlorine molecule the neighboring one or adjacent chlorine molecule. And this effect is that it causes a dipole in the neighboring one without them ever touching each other. So it's a bit like magnets. And so we use that word you might remember from GCSE magnetism, which is induced. So we say this induces a dipole in the neighboring chlorine molecule. So they've not actually ever touched each other, although gas molecules can. That isn't how this works. They don't have to touch each other. There's a repulsion and an attraction, and that induces a dipole in the neighboring chlorine molecule. And now for the third mark, we just need to describe what that is. And that is the weak force. A weak force, it's like an electrostatic force, isn't it? A weak force of attraction forms between the delta positive and delta negative chlorine atoms on neighboring or adjacent molecules. Oh my days, that was long. Right, so the first 2 marks are really for describing how the dipole arises in one chlorine molecule, and then how it causes the dipole to arise in the second. And then once those two dipoles are formed, the attraction can form between them. And that's the 3rd mark. And here we go. Let's move on. Give an equation for the reaction of chlorine with water. Give a reason why chlorine is added to drinking water. So chlorine plus H2O. And there's a couple of different ways of writing this. It's a reversible reaction, and that is going to form hydrogen chlorate, which has bleach-like properties, and hydrogen chloride. Now, is that balanced? I've got 2 chlorines, got 2 hydrogens, and I've got a no. I believe that's balanced. Okay, we'll go with it's balanced. I'll let someone tell me in the comments if I've screwed that up. Right, next question. What's the reason why we add chlorine to drinking water? To kill bacteria. It's really to kill pathogens, but it's easy enough just to kill bacteria, isn't it? There we go, sterilize the water. Chlorine reacts with cold aqueous sodium hydroxide in the manufacture of bleach. Give an equation for this reaction. So we're just going to do chlorine plus sodium hydroxide like that. And we are going to go to, instead of hydrogen chlorate, we're going to form sodium chlorate like that. And we're going to form water. And what else are we going to make? Going to make, oh, I need sodium chloride as well, salt. Oh my gosh, I couldn't squeeze it all in. Sorry about that. Okay. Yeah, that looks good. It's just not balanced, is it? I've got 2 chlorines. That's cool. Oh, I need a 2 here because we need 2 sodiums. That creates 2 oxygens and 2 hydrogens. I've got 1 oxygen there, 1 there, and 2 there. Yeah, lovely bubbly. That is balanced. Lovely jubbly jubbly. Okay, let's move on. Now, sometimes in the old AQA syllabus, before I move on, he says, let's move on. And he goes, oh, in the old AQA syllabus, you used to have to know the equation for the reaction of chlorine with hot sodium hydroxide. You don't anymore. The difference is it forms sodium chlorate where the chlorine atom has a +5 oxidation state, whereas here with oxygen -2 and sodium +1, the chlorine's in a +1 oxidation state. So this is like a sodium chlorate with a 1 in the Roman numerals for the chlorine for its oxidation state, but you can get sort of sodium chlorate where it has a +5 charge, and that would be if we were using hot sodium hydroxide, which we're not. But here we go. Just in case you ever wanted to know that. Oh, I bit my tongue earlier, so if you hear me going, that's all right. It's not because I'm some kind of lunatic. Well, I'm a lunatic as well, but there we go. Question 2, which pair of solutions, when mixed, reacts to form a dark brown solution? So we're dealing with group 7. What in group 7 do you know has a dark brown solution? I'm kind of looking for iodine, really. You know, iodine is a dark brown solution, isn't it? Black grey solid, but dark brown when in solution. You've all seen iodine solution. Well, if you've done biology, you've definitely used it. So we've got sodium fluoride plus chlorine. What's going to happen there? Nothing, no reaction because chlorine can't displace fluorine. Fluorine's more reactive. We've got sodium chloride plus bromine. Again, no reaction. Bromine's not more reactive than chlorine, so it doesn't displace it. So we've got no color change going on here. We've got sodium bromide and chlorine. Chlorine is like a pale green, pale yellow. When it displaces the bromine, you're going to get a kind of orange solution forming with the bromine being displaced. It's more likely to be down here because it says dark brown. If it said light brown, C could have been the answer because you're going to get bromine displaced. But here, bromine is going to kick out the iodine because bromine is more reactive. It's going to displace the iodine and you're going to get I2, a dark brown solution. So the answer is D. Gosh, I am waffling on here and extending these. I've got a cold as well. last few videos I've made, I'm just like, the last couple of weeks of videos I've made, I sounded like I'm dying. Question 3, some solid sodium halides are reacted with concentrated sulfuric acid. Which solid sodium halide does not produce a sulfur containing gas as one of the products? Sodium chloride, sodium bromide, sodium iodide, and sodium acetate. What you have to know with these, you have to know these reactions all off by heart. Well, you have to know these three. You don't really have to know the bottom one. You have to know these three, and it's really to do with the reducing ability of the different halide ions. So chlorine is not as good as bromide at reducing things, and bromide is not as good as iodide at reducing things. So you get the most products with the iodide. So which solid sodium halide does not produce a sulfur containing gas? It's going to be A. And the reason, chloride ions are not as good as reducing as the bromide ions or the iodide ions or this acetate or whatever that is. That would be the most reducing ion there. So yeah, it's the chloride ions. And if you want the equation, because you're like, oh, give me the equation, I'll show you the equation. So it's sodium chloride plus, what did we say? Sulfuric acid. And what happens here, this is the one that's not a redox reaction. We get hydrochloric acid formed, and we get, now you've got a choice here. You can write sodium sulfate or sodium hydrogen sulfate. I always write sodium hydrogen sulfate because if I do that, NaHSO4, I don't have to double. It balances better for me when I do that. That's just better for the old balancing job. Yeah, enough whiffle waffle. Um, and here we go. I think that's it. Yeah, that's it, isn't it? Let's just sort of substituted that and that. Yeah, there we go. So that is with the sodium chloride. If it was sodium bromide or iodide, you don't get the hydrogen bromide or the hydrogen iodide because they go on to re-react with the sulfuric acid, further reduce it, and you get like sulfur dioxide or solid, you get hydrogen sulfide or you get sulfur solid form, depending on which one of these you're using. Anywho, that's enough whiffle waffle. That's the answer. Right, on to question 4. This question is about Group 7 chemistry. A, give an equation for the reaction of solid sodium bromide. Ooh, we've just been doing the one with solid sodium chloride. So let's do solid sodium bromide with concentrated sulfuric acid to form bromine. State one observation made during this reaction and give the equation and the observation. Okay, the thing is, guys, we can do this reaction in 2 parts, or we can just do the overall for this reaction. So I'm going to do it in 2 parts. So hold your horses, and then I'm going to show the overall. So let me show you the individual, right? So you can have like sodium bromide. This is like a 2-stepper. So first of all, it reacts with sulfuric acid like this, mish bash bosh. Unlike chloride ions, bromide are a better reducing agent. So what happens here? That means that they're going to lose electrons more easily. You know, they're larger. The outer electron, that one they've gained, is further from the attraction of the nucleus, so easier to lose. First of all, it is not. It reacts in not a redox reaction. It reacts like this in a this reaction here, forming HBr. So in this situation, really, the bromide ion is acting as a base, funnily enough, is accepting a hydrogen to become a hydrogen bromide. But what happens is this hydrogen bromide goes back and reacts with the sulfuric acid. So you don't need to include this in your equation because this is in existence for a limited time. So we won't even get away with saying C misty fumes. They won't give us that for the hydrogen bromide. What happens is it comes back and reacts with the sulfuric acid. And so you will get the mark if you do these 2 reactions. But yeah, you're better off just doing the overall one. I don't know why I got carried away and shown this. And then what will happen is this hydrogen bromide is going to react with the sulfuric acid again, and you're going to get Br2 plus SO2, sulfur dioxide, plus how many we got? We've got 2 H's, H there. On my days, I need to balance this up. You're going to get plus H2O. Geez, I should balance this. Well, this isn't balanced. I need 2 HBRs, don't I? And I need 2 waters. Okay, this, you will get the mark for showing this equation in 2 parts. But really, why bother? You can show it all in one part. So how we can do that is we can get rid of this and say, okay, yes, HBr temporarily forms, but then it gets wiped out in a kind of second step. So we don't really need to show that. We can just show NaBr plus sulfuric acid goes to, whoopsie, NaHSO4, my days, plus Br2 plus SO2 plus H2O. But now I need to balance it up properly. So we're going to need, I'm going to need two NaBrs. I'm going to need three of these bad boys, two of these. It would have been easier if I'd just done it as sodium sulfate, but never mind. I think that's all right. That's all balanced, right? Yeah, that's balanced. Yeah. Yeah, it's balanced. Okay, so a bit hard for you to see there, but this is the overall equation. You don't show the HBr. So what's an observation? What one of these can we actually observe? I haven't put state symbols in. I wonder if they'll penalize me for that. Because it did say solid sodium bromide. So that would be solid. Uh, all acids are aqueous, so AQ. We're going to form bromine, but that is going to be in solution, right? Because we've got water knocking about and bromine dissolves. That's going to be in solution. We're going to have sulfur dioxide gas coming out, so some bubbles of gas. Will we get away with saying bubbles? Probably not. We've got sodium hydrogen sulfate, and that is going to be um, yeah, like that. Now, the bromine, I guess we're going to see it's in solution. We're going to see, unless it's bromine gas, difficult one. So we're either going to see an orange solution. Oh my gosh, I'm writing in blue as well, just to confuse things. So we're either going to see an orange solution as our mark, or we're going to see like a brown, red vapor, which would be it coming off as a gas. So it really depends whether we needed to do state symbols. I guess I should really check the mark scheme on that. But there we go. One mark for that and one mark for that. So you're going to be able to see the bromine, which is going to be an orange solution when it's dissolved in water, or orange brown solution, like light brown, not dark brown, that'd be iodine. And you're going to see, or a brown red vapor if it vaporizes from the solution. Okay, let's move down. Let's move down. A solution that is thought to contain chloride ions and iodide ions is tested. Okay. Dilute nitric acid is added to the solution, right? Aqueous silver nitrate is added to the solution. Cool. Pale yellow precipitate forms, so you should know your halide ion tests here. Excess dilute aqueous ammonia is added to the mixture. Some of the precipitate dissolves. Okay, cool. And a darker yellow precipitate remains. Give a reason for the use of each reagent. Explain the observations. Give ionic equations for the reactions. And it's got to be a fat 6 marker. Oh, it's a 5 marker. Okay, 5 marks. So let's get into it. So first of all, why add nitric acid? So why do we add HNO3? Why do we add nitric acid? That is to remove impurities. So I want to say HNO3 removes carbonate impurities, also hydroxide impurities. So it's going to remove those. Why do you want to remove those? Those would also give a white precipitate. Okay. So that would kind of like give you a false positive or whatever you call it. It'd mash up your results. Now, aqueous silver nitrate is added to the solution. Well, aqueous silver nitrate is going to produce a precipitate. So AgNO3 produces a white precipitate. Oh my God, I can't spell. So that's something Roman, precipitati. Okay. AgNO3 produces a white precipitate with chloride ions, right? You need to know that. Of course, what's it producing? It's producing AgCl, which is a solid precipitate. So it's going to make that, or a yellow precipitate. It actually goes cream with bromide ions, but we're not dealing with those here. Or a yellow precipitate with iodide ions, in which you're going to get Ag I as a solid. Okay, so we've explained why, and if you think about it, that's why we got a pale yellow precipitate, because we got a mixture of the white chloride ion precipitate and the yellow iodide ions. So, whoopsie, we get a pale precipitate days as we have a mixture of AgI and AgCl. Days, like when I'm typing like this, it is full of mistakes. Look at that again. Precipitate. Okay, so we get a pale precipitate as we have a mixture. So what we've got going on here, we've got the yellow iodide ions or silver iodide, and we've not ions, it's in a precipitate there. And then we've got the silver chloride together, which is white, and together white and yellow make pale yellow. Now, what happens next? The excess dilute ammonia is added to the mixture. This dissolves the so dilute ammonia in excess dissolves the silver chloride. Um, but not the silver iodide. So the yellow precipitate remains. That's why it goes like a darker yellow, because the yellow precipitate remains, whereas the white precipitate has dissolved. And now we need to bus out the equations for that, because we've kind of explained the observations. We've explained the observations, so that's going to be at least 3, maybe 4 marks. We want to bust out the ionic equations. It's kind of like okay, so for the ionic equations, I'm going to do them here because I'm running out of space, or maybe I can get one down there. So let's bust out the ionic equations. So what I want to do is Ag plus Cl minus goes to AgCl. And if I'm going to do state symbols, then ions are always aqueous. So if you have 1, 3, and ions, always aqueous. So bish, bash, bosh there. And then we've got the Ag plus, that's from the silver nitrate, plus the iodide ions, and we get the AgI. Okay, now it says, does it say all the give ionic equations for any reactions? Yeah, well, we've got a reaction, haven't we, when the um, chloride ions dissolve. So we can show that as like this. So when the chloride ions dissolve, obviously the iodide, silver iodide doesn't dissolve, so there's no reaction. But when you take the silver chloride and you add it to excess ammonia, it's going to make an ammonia solution, it tells us. It says there, where is it? Aqueous ammonia. So we know that's AQ. You're going to get silver ions, which you can just write as silver ions with a plus charge there, or it forms a little bit of a complex here, and we can do that. So if we want, we can do that. Or you could just write Ag plus and Cl minus. They go back basically into being aqueous again. So both of these. So we get aqueous silver ions, and when the ammonia dissolves that there. Oh, it's not balanced. I need 2 of them, so I need a 2 there. How many chloride ions? Just 1. Yeah, cool. So those are your 3 equations. So that will do for all the equations, and that will get you the marks. Maybe the equations are 2 marks. 1 for that one for both of these ones. Okay. Right. Let's zing on. Question 5. This question is about group 7 elements and their compounds. Chlorine is used to treat water even though it's toxic to humans. Give one reason why water is treated with chlorine. So we know that reason, don't we? It's to kill bacteria. So I'm just going to bust that again, to kill bacteria. You can say to sterilize the water, to kill pathogens. Explain why chlorine is added to the water even though it's toxic. So we're going to say the risk to humans is very small. So it's like, yes, same reason they add fluorine. People get really upset about governments or states adding fluorine to tap water. But again, it kills bacteria and all those horrible diseases that you get out your tap water if they didn't add fluorine. But there is a small risk from adding these halide ions to the water supply. Okay, give an equation for the reaction. Oh, and the last one, we've done this one 8 million times. So it's chlorine with cold water. So by the end of this pack, you should be like, yes, that comes up in the A level. I'm all over it. So Cl2 plus H2O goes to hydrogen chlorate. What was the other thing it makes? Hydrogen chloride. And there we go. And it's in this reversible reaction where it's reforming chlorine and da-da-da. Well, you smell chlorine coming off the swimming pool, can't you, when you walk in there? Because it's kind of like some of it's vaporizing as it goes that way and blah, blah, blah. And then we got this bleaching effect of that, which is killing the bacteria and whatnot. Okay, cool. Let's smash a mark on for that and move on. Oh, have I even balanced it? I've got two H's. I've got a Cl, got a Cl, got an O. Yes, balanced. Nice. Oh, yeah. Bish, bash. Let's go. Oh my gosh. Solid sodium iodide reacts with concentrated sulfuric acid to form iodine and sulfur in a redox reaction. Give a half equation to show the conversion of iodide ions to iodine. Give a half equation to show the conversion of sulfuric acid to sulfur. Give an overall equation for this reaction. Identify one other sulfur-containing reduction product formed when solid sodium iodide reacts with concentrated sulfuric acid. Half equation for the conversion of iodide ions to iodine. Half equation for the conversion. Blimey. Yeah, we get the idea, right? So I need all right, let's do it. Let's do it all. Let's do it. Let's do it. They're going to want the full equation as well. We'll do that underneath. So half equation, really easy. Iodide ions to iodine. So we're going to start with I minus, it's iodide ions. We're going to draw an arrow. We're going to write iodine. It's diatomic. You should know that. So that means I need two of these. And what are these? These are electrons. So I need to show them being lost over here. And of course, that's oxidation, isn't it? The iodide ions are being oxidized, which is why iodide is quite a good reducing agent because it's easily oxidized and gives its electrons, reducing other things. Half equation for the conversion of sulfuric acid to sulfur. So what we want to do here, they've told us that we got sulfuric acid on this side of the equation. I'm going to draw an arrow, leave a big fat bit of space. You can always move that over after. And then it says to sulfur. Now I just need to add in the other products. So the fact that I have oxygen here when you're doing half equations, that always means you're going to make water. So I've got 4 oxygens, so I need 4 waters to make them 4 oxygens. Okay. Now, I don't know why I've left such a big fat space there. It looks a bit dumb. I'll close that up in a second. So I've got, what else do I need? Sulfuric acid to sulfur. That's it. It's going to make 4 waters. But we're not balanced. I'm missing some hydrogen, so I'm going to add 6 hydrogens here. Now, is there anything else? Going back to this one, by the way, you have to check whether they're electrically balanced. See, it's 2 minus there, and I've got 2 minus electrons there, minus 2 on each side. The equation is balanced. If I come down here, I need to now check that it's electrically balanced. I've atomically balanced it, as in there are 8 hydrogens there, there are 8 hydrogens there. There are 4 oxygens there, 4 oxygens there. There's 1 sulfur there, 1 sulfur there. So it's atomically kind of balanced, but it's not electrically balanced. I've got 6 plus here, and I've got no charge here. So I need to get rid of this 6 plus on this side, and that's why I'm going to add 6 electrons to this side. Now you might say, oh, why don't I add 6 electrons here? Well, that would have become 6 minus and 6 plus. So that wouldn't be balanced. So I have to add the electrons there to balance it. And what I need to do is zing this over because this here is too far away. I've got a double plus situation going on. Cool. Nice. Let's move on. Let's move on. Let's move on. We're probably going to have to combine these. And if I'm going to combine these to make the overall equation, I'm going to write it down here. I'm going to write it in blue just so it's like slightly different. What we need to do is look at the number of electrons and see that this half equation has 6 and this has 2. You need to balance the electrons when you're creating a whole equation. So I'm going to times everything up here by 3. And I'm going to do that and whack it all in and then whack all of that in. And that's your overall equation. So I'm going to go 3 times 2 minus iodide ions. I've got 6 iodide ions now because I times them by 3. I've just going to keep everything down here the same because we didn't multiply that by anything. So 6H plus. If you write the electrons in, they're not going to count because they're going to cancel because I've now made 6 electrons, so they're going to cancel either side. But we'll write it all out and see how it goes. Right, now I need 3 times I2. I've got to put big fat 3 in front of that because we multiplied it by 3. I'm going to have 6 electrons. Now, I can already jump all over those electrons and cancel those because we don't want those, so I shouldn't really include those. I've just put them there to show. Okay, now I just need to add these in then. So 3I2 plus S plus 4H2O, and that is it. So once again, you can get rid of the electrons, you don't need them. So it's 6I minus plus H2 SO4 plus 6 hydrogens goes to 3I2 plus S plus 4H2O. And I should just make sure it's electrically balanced. There's 0 charge on the right. I've got 6 plus hydrogens here, but I've got 6 negative iodide ions. That's why. So they're all balanced up and it's 0 charge. So lovely jubbly. Do your double checks. Check if it's atomically balanced or elementally balanced, however you want to word it, and then check if it's balanced in terms of electric charge. Oh, what's the other sulfur-containing reduction product? Well, there's a whole bunch probably we can do here. Sulfur-containing reduction product other than sulfur. I wonder if we'll get them up for sulfur dioxide or hydrogen sulfide, because both of those can form. And yeah, they are both in reduced states. So this is only iodide is going to reduce it down to that, and that's the eggy smelling one. I think that goes to a sorry, -2, and here this is +4. And of course, when it's in sulfuric acid, the sulfur, maybe that's +1 and they're -1, whatever, but the sulfur is +6. So you can see whatever is being reduced, the sulfur is gaining electrons, it's being reduced. Okay, and it can get even more reduced to hydrogen sulfide with iodine. So I think you can have SO2. So we didn't have that up there, and you can have hydrogen sulfide. So either of those should be good for the mark. And I already did the overall equation. Okay, right, let's move on. A student completes an experiment to determine the percentage by mass of sodium chloride in a mixture of sodium chloride and sodium iodide. The student uses this method. 6 milligrams of the mixture are dissolved in water to form a solution. An excess of aqueous silver nitrate is added to the solution. This forms a precipitate containing silver chloride and silver iodide ions. Oh no, or silver iodide, sorry, not ions. Excess dilute ammonia solution is then added to the precipitate. The silver chloride dissolves. The silver iodide is filtered off from the solution and is then washed and dried. The mass of silver iodide obtained is 315 milligrams. Silver nitrate is added to the solution. Suggests why an excess is used. Excuse me while I have a drink of coffee. So this is to ensure the reaction goes to completion and we have no chloride or iodide ions left in the solution. They've all reacted to form precipitate. Okay, so reacts fully to ensure no iodide ions or chloride ions are left. They have all formed precipitate. Okay, so we want to make sure they've all precipitated out. So we're going to add excess. Now let's move down and see what the questions are. That was C. Calculate the amount in moles of silver iodide obtained. So we want to work out how much silver iodide is obtained. So we had 600 milligrams to start. The mass of silver iodide, is 315. Calculate the moles of silver iodide. Oh, well, that's easy peasy, isn't it? They've given us the max. The mass was 315 milligrams. So if I divide that by 1,000 to turn into grams, that's 0.315 grams. I'm then going to do the old mass over AR or MR, however you like to write it. So we've been given the AR is 23, so they're really being nice and generous here. 234.8, and that is going to give us our number of moles, which is N. 0.315 divided by 234.8 equals 1.34, going around maybe 2 times 10 to the minus 3 moles. And that is of silver iodide. And that is going to get me, I'm going to write that down because I'm probably going to need that later on. So there we go. Beautiful. Clear that. And then let's go down. Amount of silver iodide. Now calculate, using your answer to D, the mass in grams of sodium iodide in the mixture. Cold is whacking me out. Essentially, look, if we did the reaction, the sodium iodide was in the original mixture, right? The original mixture contained sodium iodide and sodium. What was the other thing? Was it chloride? Oh my God, I'm losing the plot. Sodium iodide and sodium chloride. They did a reaction, and the sodium iodide reacted, right, with the silver ions. It was a one-to-one reaction, okay? So I know this is some bogus equation, but yeah, it's one-to-one. So the silver iodide, um, we know what the moles of that are because we just calculated, whatever that means, calculated the moles of that. What was it? 1.342 times 10 to the minus 3. We just calculated that, and we know that it's a one-to-one with the silver nitrate. Okay, one-to-one reaction. So we know I'm also going to have 1,342 times 10 to the minus 3 of that. You can see it's only a one marker, so it's got to be dead easy. So we got that many moles of sodium iodide. So I just need to times that in the old equation where I do MR times moles. It's going to give me the mass. So I want to do that times 149.9. And that gives me, rounding, 0.201 grams of sodium iodide in the mixture. Would have been an easy mistake to make with this. There could have been a mistake where you got yourself mixed up. But yeah, they're basically asking you how much of sodium iodide. We worked out the silver iodide, how much sodium iodide was in the original. All right, we've worked that out. Let's move on. Calculate, using your answer to part E, the percentage by mass of sodium chloride in the mixture. Right. Now, if I just put that all back, look, we worked out now that there was 0.201 of this, 0.201 of that. How much was this? This was 600 milligrams, which is the same as saying 0.600 grams. So it's the same as saying that. And we know that 0.201 or 201 milligrams, and that's 600. If we convert that back to milligrams, yeah, blah, 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 whatever. We're going to do that. So let's work it out. So we had 600 milligrams of sodium iodide and sodium chloride. We want to take away the sodium iodide, which we just worked out was 201 milligrams. You could do this like this. You could do that. Or if you prefer, you could do this. It does not really matter which one you prefer. So that is grams if you're a grams person. If you're an mg, if you're a mini g, then you can use mg. And that's going to give us 399 milligrams. So the percentage of sodium chloride in the mixture is 399 over 600 times 100. And it's like 66.5%. Now, again, you get the same answer if you did 0.600 over 0.201 times 100. So same to, oh, sorry, not, what am I on about? If you did 0.399 over 600, God, I am absolute, my voice is going. My voice is gone. Jeez, this cold, man. What you gonna do? Okay, question 6. Which property increases down group 7? The ability to oxidize, the boiling point, the electronegativity. First, I'm just going to cut to the chase. It's the boiling point, right? I mean, you get a nice, easy one like that. It's the boiling point because basically, when they're big, as they get bigger, the intermolecular forces, the van der Waals forces, get with the more electrons, those dipoles get more exaggerated and get bigger, and then you get stronger forces. So the bigger halogens, iodine's a solid at room temp, chlorine's a gas. So boiling point, definitely Bosch. Okay, question 7. Which equation shows a redox reaction that does not occur? So let's have a little butchers. Got bromine plus 2Ki goes to I2 plus 2KBr. Chlorine plus 2Ki goes to iodide. Okay, basically, which one doesn't occur? So we're saying, can bromine displace iodine? Yes, that does occur, so that's not the answer. Can chlorine displace iodine? Is chlorine more reactive than iodine? Yes, that does occur. That's not the answer. Is chlorine more reactive than bromine? Yes, chlorine will push that bromine out. That is not the answer. Is iodine more reactive than bromine? No, iodine's getting down, fourth one down. It cannot beat up or push out or displace bromine, chlorine, or fluorine. So this does not occur. Um, let's go. Let's do one more question, and that'll be the end of this part to the Group 7 halogens. This question is about sodium halides. State what is observed when silver nitrate solution is added to sodium fluoride solution. Well, I don't believe they form do they form a colorless solution, or do they also form a white precipitate? I don't believe they actually precipitate. So no precipitates formed. I think we're just going to get a colorless solution. So I'm going to go a colorless solution, and then you can punch me in the face if that's not what it says on the mark scheme. Okay. Let's move on. I could probably say white precipitate. Yeah. Probably going to punch myself in the face. State one observation when solid sodium chloride reacts with concentrated sulfuric acid. Give an equation for the reaction. State the role of chloride ions in this reaction. So we've done this one. Solid sodium. Okay, right. This one here, I'm going to start with the equation because that's important. So NaCl. You have to know these. So if you're going through this and you're like, oh man, I ain't got a clue with these, then you really need to revise this section of your year 12 chem, because this can come up in the in your A2, your actual A-level exam. So sodium chloride plus sulfuric acid. I go for this. You don't have to do this one, by the way. I'm going for this one. I'm doing the older sodium hydrogen sulfate. You can go Na2SO4. Some people find that one a lot easier, and it makes HCl. So solid AQ, AQ, and then this one is a G bad boy gas, hydrogen chloride gas. Now, observation, I'm going for misty fumes. When any of the halide gases like that, the hydrogen halides, you can see some misty fumes. Now, what's the role? This one's quite interesting, and this will catch some people out. What is the role of the chloride ions? Well, check them out. They're -1 charge there. Then when we come over here, they're -1 charge there. So I don't think there's been no redox. Let's check the sulfur. The sulfur is, that's +2, that's 8 minus. So the sulfur is +6 here. Over here, sodium's +1, hydrogen's +1. Sulfur here, peeps, is also +6. This is not a redox reaction. Nothing is changing its oxidation state. This is actually the chloride ions. The only thing we can say about them, what's happened to them here? They've gained a hydrogen. What are you called if you accept a hydrogen? They have accepted a proton. Accepted a proton. What do we call things that accepted a proton? Yep, we call it a base. Or you can just say, if you don't like calling chloride ions a base, you can call it a proton acceptor, if you want to say that. It's acting as a proton acceptor or a base. Okay, there you go. So bish, bash, bosho. Boom. Right, enough of that. Let's move on. Give an equation for redox reaction between solid sodium bromide concentrated, blah, blah, blah. I think we might have already done this one, but anyway, here's the equation. So you've got to know this one as well. So we got, right in it. Let's start with the solid sodium bromide. So NaBr, it is solid. Smashing, we're going to say why this is a redox reaction. Ooh. Unconcentrated sulfuric acid. Oh God, I'm dying. This is long, isn't it? Long, 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 bum, 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 long, long, long. Okay, so we've got solid sodium bromide plus aqueous blah, sulfuric acid. This, why do I do it, Tom? I should just do, oh no, I'm going to do sodium hydrogen sulfate. I always stick to my guns. This one is not easy to balance. So you're going to get sulfur dioxide, you're going to get bromine, and you're going to get water. and then I need to balance it. You have to know these bad boys off by heart. What is it? 3 of them. 2 of these. That 3 don't look good, does it? Let's get rid of that. Put a tiny baby plus in. And then what am I making? 2 sodium hydrogen sulfates, 1 sulfur dioxide, 1 bromine, and 2 waters, which I'm going to struggle. That's really ugly. Okay, so explain why this is a redox reaction. Check the sulfur. Sulfur is +6 in sulfuric acid, but in sulfur dioxide, it's +4. So if I want, I'm just going to go with that. Okay, sulfur gains 2 electrons, goes from +6 in H to SO4 to +4 in SO2, sulfur dioxide, right? That's one way of explaining it. So what's happened to it? It's gained electrons. It's been reduced. If I want to say it has been reduced, oh, let's add that in. It has been reduced. Now, there's also been oxidation. It's not a redox reaction unless there's been oxidation. So let's explain where the oxidation is taking place. Well, -1 bromine in its elemental form is 0. So bromine has, or bromide ions have lost electrons. So I can say bromide has lost an electron to become bromine. It has been oxidized. I'm sure I've gone overboard there, but there we go. If I want, I could have done the oxidation states. It's gone from, bromide's gone from -1 to bromine where it's 0. Okay, so it's been oxidized. So there we go. Lovely jubbly. Don't forget you'll be getting marks for the equation as well. Actually collapsing. State what, this is the last question, I'm totally finished now. State what is observed when aqueous chlorine is added to sodium bromide solution. So, oh, I'll give it an equation. So I'm going to do the equation first. So first of all, you got chlorine, right? And they're telling me it's AQ, telling me the chlorine's AQ, right? And it's being added to sodium bromide solution, right? Easy. What's more reactive, chlorine or bromine? Chlorine is further up group 7, it's more reactive. So it's going to displace the bromine. What we're going to end up with is sodium chloride in AQ. And we're going to end up with bromine being displaced, aqueous. So what we're going to see is the color of that bromine. That's going to be our observation. So I'm going to see an orange solution. You probably can say brown, light brown solution as well. Orange, brown, similar. So I'm just going to say orange solution forms. That's what we're going to see. Ionic equation. This isn't really, I've done the normal equation. The ionic equation, we don't want to include spectator ions. So anything that has changed their physical state, they're all aqueous, so none of them have, or their oxidation state. Well, chlorine's gone from 0 to -1. So I'm definitely putting my chlorine in here and it's going to be Cl2. And then my bromine has gone from -1 to 0. So it is also not a spectator ion and I need to include that. And if I was going to balance this, I'd need a 2 there and a 2 there. So I'm going to need 2 bromide ions. And we're going to go to 2 chloride ions plus bromine and smash all of those in. Yeah. And if you're, the sodium and stuff, that's a spectator ion. It hasn't changed its oxidation state. +1 there, +1 there. So sodium is a spectator ion. It hasn't changed oxidation state or its physical state. It's aqueous in both. So there we go. That's going to get you the marks. All right, folks, I'm going to do another part to this. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.